Hello and welcome back to my channel. So this is going to be a new sequence of videos I'm going to be putting together, mainly for doing Matlab. And as much as I can, I'm going to try to code up everything from scratch. So start with almost nothing and write up all the code as I can, unless it gets to be fairly complicated code, and then it'll be more of a code tour and we'll walk through little bits and pieces in the lectures. This is also the first time that I'm playing with OBS, so this is meant to help streamline these lectures, and so there's not going to be really much editing in here. And so it's going to be maybe a little bit more raw. Maybe I'll get frustrated at some points, and and maybe I'll get stumble and things like that, and well, that's mostly going to be in here. But that's the way it goes. That's research and that's coding. And so I want to help you guys learn how to code in Matlab if you would like. And today we're going to start with something really simple, and that is going to be RBF interpolation. So we have an interpolation problem, and it looks something like this. So here we have, and the dashed line is our original function, which we don't know. That's why it's dashed. But what we do have is we have the data. And so we have these points that were sampled at the x coordinates x1, x2, x3, x4. That really should be on the x-axis, but like I said, unedited. And their height represents whatever f was at that point. And so this is going to be a one-dimensional interpolation scheme, just because it's quick to plot and whatnot. But in all honesty, it's not going to be that different than what you would do for a higher dimensional integration scheme with kernel functions. And maybe next time I'll show you how you can convert from one to the other, and also a good way of getting sample points. So what we're going to do is we're going to make up some other function. That's that orange curve there, and that's going to be our interpolation function. And that interpolation function is going to match the function exactly at those points, but might not completely agree with the function itself. And so we saw in a previous lecture I did that you can have things like Runge's phenomenon, where you can have perfect interpolation at those points, but you might blow up everywhere else. And so what we're going to do is we're going to use kernel functions, and we're going to see how well it does here. So like I said, we're using kernel functions, and I didn't write the kernel function that we're going to use, but this could work for any collection of kernel functions. And so, but here we're going to use Gaussian. So the Gaussian is the exponential function raised to the -1/mu times the absolute value between x and y. And so that would go here, instead of x and x1, we'd have the absolute value of x minus x1. And then you take the absolute value, you square it, and there you go. That's the Gaussian RBF. And you choose mu in some credible way, usually about the size of the difference between your data points. And yeah, and that's what we're going to try to do. So we need to figure out some way to figure out what these W's are that sit on these kernel functions. And that's what this brings up. So here we have the pairs x1 and f of x1, x2, f of x2, all the way up to xm and f of xm that we want to interpolate. And we're going to have an interpolant made out of our kernel functions. That's that Sx I wrote up there. And so how do we determine these weights? What we're going to do is we're going to evaluate Sx at x1, x2, x3, etc. And we're going to separate the weights from the kernel functions. And we're going to take the kernel functions and write them as a row vector. And we're going to take the weights and write them as a column vector. And so what we can do is we end up making a matrix. And so we take a full stack of these, and that matrix is called the Gram matrix. And it turns out that it's going to be invertible for almost every kernel. Strictly what we need is a strictly positive definite kernel, but almost every one you're ever going to really use is going to be strictly positive definite. And even if they are not strictly positive definite, there's other things you can do. But in this case, we're not going to worry about that. The Gaussian is a strictly positive definite kernel, so this isn't going to be an issue. And another lecture, I'll tell you how to handle it otherwise. So what we're going to do then is we're just going to invert that matrix on the other side against all of our y values, or f of x's. And then that'll give you the weights. It's pretty simple. And it turns out that, this Gram matrix actually is the pairwise inner products between kernel functions centered at particular points. And so simultaneously, we're not only doing this interpolation, but we're also going to be doing a projection onto the subspace spanned by the kernel functions centered at these points. And so in a sense, this is the best possible approximation you can get if you're thinking in terms of the Hilbert space norm. So anyway, that's a lot of chatting, and why don't we go ahead and jump into the actual code. Okay, so here I have a little bit of Matlab started up already. Here you can see that we have the function that we want to interpolate, and this is sine plus x cubed divided by 5, just to make it clear. And then we have cosine of 2 pi and divided by 5 times x. There's nothing special about this function. I just went ahead and defined it so that we can go ahead and have something to interpolate. There is, in 2 dimensions, Frankie's function, which is kind of a standard bearer for a standard benchmark as far as, you know, doing any sort of interpolation, and we'll talk about that in another time. And so, let me fix the camera real quick. There we go. So what I'm going to do now is I'm going to keep fiddling with the camera, and yeah, I like that better. Okay, well, let's keep that going. Okay, so what we're going to do is I'm going to take points that we want to evaluate. So just to see what this function looks like, just so you have an idea of what our goal is as far as an approximation goes. And so I'm going to put that in here, and remember this is made as a row vector, and if I put this in here, then I'm like, if putting in f evaluated at this row vector, I need to make sure that it's reading it right. And so you can't just have x cubed as x dot cube. So this gives us entry-wise a cube along this entire evaluate thing. And same thing, and sine applied to a row vector will just apply sine entry-wise. And so that'll be fine. And so if I want, I can go ahead and plot this, but I want to mention one other thing is we're also going to have our samples. And we're looking at the interval 0 to 3, just because, and we're going to sample at every half integer. And so if you take a look at the result here, yeah, there we go. So it showed up in OBS, that's nice. We see that we have a nice curvy thing, but it looks like our samples are indicating something that's very different. And so we're going to see that our interpolation here isn't going to be the best. Of course, I mean, we're skipping like a whole lot of data in between here, and as we increase the number of samples, we're going to improve our interpolation. So why don't we go ahead and we'll start coding up the gram matrix and our kernel function. So here I'm going to say kernel function, and so for the kernel function, like I said before, it's going to be the Gaussian. And so for the Gaussian, remember, we want to have some sort of mu, and so I'm going to choose mu is equal to 0.5, and basically I'm trying to match the difference between my sample size. And I can choose to be slightly larger, but not too much larger, because then it'll blur out the data, and then the gram matrix actually ends up being poorly conditioned. And so it has to be roughly about the size of the minimum pairwise distance between all of your points, and can't be too much larger than that, or at least 2 rows will look almost identical. Anyway, so then we need a kernel, so I'm going to call this k. So it's going to be at xy, and it's going to be the exponential of -1 over mu times, we'll say, the norm of x minus y squared. And so if I were to put in a column vector for x and a column vector for y, this would actually work out fine. So it's already sort of hinting at multiple dimensions. Okay, so now we need a gram matrix. So that gram matrix is that matrix that we saw earlier, and basically it's going to be the entry-wise evaluation of our kernel functions at each of these sample points. And so it needs to be the number of sample points by the number of sample points. So we can make that by saying gram matrix is equal to zeros of size, or we'll just say length t samples, right? Piece of cake. So when you put zeros and you only put 1 entry in there, I'm going to show you. So if I put in zeros 2, it gives me a 2 by 2 matrix of zeros. So this is giving me a length t samples by length t samples matrix of zeros. But we don't want it to be zeros, so we need to fill it in. So we'll make a for loop. You can do this a lot faster than this. This is just an example. So we're going to do a for loop, say length t samples, and we're going to say for j going from 1 to length t samples, and then we just fill it in. So we're going to say the gram matrix at ij is equal to, let's see, k at t samples I, comma t samples j. And if we wanted, we could already double the speed of our code, and I could change this to being j going from I to length t samples. Then I just take the transpose of that and add it back to the gram matrix, and ta-da, we'd be done in half the time. But there's an even better way of doing that, and it's just by exploiting some matrix manipulations, but that would change for every single kernel function we use. So as long as I keep it like this, I can just change kernel function in here and get a completely different look at what the interpolation will look like. And so I'm going to keep it pretty general for now. All right, so that's our gram matrix, and we need a vector of all of our t samples, but we already have that. It's going to be f t samples, so I'm just going to call this, say, y is equal to f of t samples prime. Okay, so then in order to get the weights, so say sampled output, and so then for the weights, we're going to take say weights is equal to, I'm going to say the pseudo inverse the gram matrix applied to y. Now I'm saying pseudo inverse because sometimes our points are going to get a little close to each other, and so then pseudo inverse will use the SVD rather than the proper inverse in order to find it, and so it might work out better if you're like on the edge of not being able to invert your matrix. And so that's all I really do. And so yeah, that's our weights. So what we need to do now is we need to come up with a way of evaluating our approximation. And there's a few ways you can do this. Let's go with the simplest way. So I'm going to take, let's say, I'm going to define z, and that's going to be my output. And I'm going to say, look at zeros, going to make zeros, and I'm going to make it a row vector, and it's going to be a size of t evaluation. Where is it? T evaluate? T evaluate. And so once I do that, I'm going to go ahead and I'm going to fill it in. So we're going to say for I goes from 1 to size t evaluate. And in order to fill this in, I'm going to say, I'm going to have for j is equal to 1 to size t samples. And in here, I'm going to say zi is equal to, or well, here. All right, so basically what we need, and so we know that this interpolant is going to be a sum. So I'm going to say sum is equal to 0. We're going to add to this. And then what we're going to say is that zi is equal to whatever the sum is at the end of the day. In order to get what the sum is, we're going to say sum is equal to sum plus, and then we're going to say it's going to be our weights at j times k, and it's going to be at t evaluate I, comma t samples j. And there we go. Then at the end of the day, we want to plot it. So we're going to say plot. And there we go. So we're going to say plot t evaluate, comma z. I'm going to put line width, and we're going to make that 3. And I'm going to put in hold on, and then let's make this a new figure. And then I'm going to plot our original graph. So plot, I'm going to take what I had up here, and that was this guy. We're going to plot that. Boop. And let's make it dashed. Does this do dashed? I don't know, we'll see if it does dashed. Yeah. Okay, so now let's go ahead and push play. and see what happens. So we still have this figure up here that we're trying to interpolate, and we're trying to interpolate those little red crosses there with this new interpolation function. So let's go ahead and push play. All right, so figure 2. That did not do what I wanted it to do. Is that coming up yet? Turn figure 2 on. It's exactly the same as before. And so that did not do what I wanted. Why did it not do what I wanted? Because I broke something. And what did I break? Error in zeros, size of inputs must be a scalar. So what did I do? Oh, size should be length. There we go. So I just had size in there, which gives us a 2-dimensional vector, one telling us the rows and one telling us columns. Length will tell us, if it's a vector, just how long it is. All right, now let's see if this works. Boom, there we go. And something went drastically wrong. Let's see. So you can see that here we have the dashed line of our function we're trying to interpolate. We didn't even get the interpolation sites, so something went wrong here. And let's see if we can find it. Could it be mu? I don't know. Let's see, what is the gram matrix rank? Rank 7. See size of gram matrix. 7. Okay, well that's the right size. Let's see, what is y? Let's take the y. Well, those are roughly the things I wanted. And let's take a look at FT samples. Boop. And same values. Well, that's what it should be. Okay, so that means things are a little bit more complicated than I thought it would be. Let's see. What went wrong? So we have an exponential in here. T-evaluate at I. That is okay. And sum equals sum plus. That should be fine. Size of T samples. Oh, there we go. Size T samples. Should be length again. And that should be length here. There we go. Okay. If I wanted, I could just do size, and so for instance, I could do this also, if you're not familiar. That would also give me, or is it this one? I don't know. So, but anyway, 1 gives you the size, comma 1 will give you like rows, and size comma 2 will give you columns. Or if you're not sure which is which, just put length. So let's try this again. Boom. There we go. That's a lot more like what I wanted. And why don't we go ahead and change this again. Boop. Boop. Sorry, you're not seeing the answer. Dump. There we go. So yeah, here we go. That's the curve that we wanted, and it does look pretty close to those interpolation points that we saw. So if I hide this figure real quick, you can see those interpolation points. It's going right through them. So that's pretty good. But we can do better. And why don't we go ahead and plot the interpolation points on this guy too. So just so you see. Boom. All right, so close that. And try again. Okay, so now you can see the interpolation points are now these little orange pluses, and so that's good. Now let's increase decrease the distance between these samples so you can see how much it improves. So I can take it down to, say, I'll have the distance, and let's push play. And you see, doubling the number of points, now we have almost a perfect interpolation. It's actually strikingly good. I didn't think it would be this good. But yeah, so now that I included all those half points, I now actually including all these peaks and other things that we wanted, and you see that it's turning out fantastic. And so yeah, this is kernel interpolation, and this is doing it with the Gaussian RBF. Now why don't we change the kernel function to something else? And so instead of the Gaussian RBF, why don't we turn it into the exponential dot product kernel? And so it's going to be x transpose times y. And here I'm going to set mu. Well, it doesn't matter too much. It could be 1 or 3 or something like that. Basically, you just want to make sure that x transpose x doesn't get too large, and if it does, then an exponential of something really, like exponential of something raised to 20 is going to be really, really large. So you want to kind of cram it down into something reasonable, like 1 or 2 for after you divide it by mu. So here I'm just going to choose 2, not quite cram it down into 1, and let's see what we get. Boom. Okay, so we see that the exponential dot product kernel didn't do quite as well as the Gaussian RBF. Now the Gaussian RBF actually enjoys what is called spectral convergence rates, which means that it's converging at something like e to the 1 over h roughly, and so, or e to the minus 1 over h. And so then as h goes to 0, 1 over h goes to infinity, but you have a minus sign in there, so that's going to make it go to 0 really quick. And I don't think there's any sort of convergence rate estimates for dot product kernels. We know that they work well, and it works pretty well here. I might be able to get away with adjusting the mu to make it work even better. Let's see, if I choose 1, does it work better? Nope, that did not work better, and I guess you can't see it. Hold on, let me fix this. Sorry, growing pains. There we go. So here's the exponential dot product kernel. All right, so you see it didn't quite work out. There's a few points that is sort of missing, and we'd like to correct that. And so by adjusting mu here, I can try to see what else happens. So if I change it to 3 or 6, let me change it to 6. Let's see, and there we go. It's terrible. It's getting worse and worse, and so that's not a good thing. And if I take it down to say 3, let's see, boop, it did better with 3, and but it's still not perfect. So the exponential dot product kernel is going to require a few more points in order to get a better sample, a better estimate. So if I change it to 0.1, for instance, it's getting better, but now I need to adjust the mu again because it's funky. Let's see. There we go. So now we get practically perfect. And so it takes a little bit of wrestling with different kernels and getting different results. And yeah, I mean, that's just going to be life. There will be places where the exponential dot product kernel does a lot better than the Gaussian RBF, and vice versa. The Gaussian RBF, though, is a really good general purpose way to go. It does get trickier to code up quickly. The way I did it, this is what my friends and I call slow code. And so you don't want to make the grand matrix like that. That takes way too long. And so in a future lecture, I'll tell you how to do it faster. And yeah, and you really don't want to do it this way either. There's a much faster way to go about this. Here we didn't have a whole lot of points, so it didn't really make that much of a difference. But when you're doing a lot of things with, like, you know, DMD, and you're working with like 80,000 dimension vectors, it really matters. So anyways, yeah, thank you for sticking through sort of my growing pains lecture here on my channel and working with OBS. It was kind of fun. The video quality coming from my camera is going through EOS webcam utility, and so that means it's actually dropping the resolution a bit. And so I have an adapter to come in, so I get straight HDMI from my camera, so then I'll get a 1080p back. But you know, I just wanted to give this a try while I still had everything set up, and might as well make a video out of it. So thanks for watching, and if you want to see a lot more Matlab lectures, please do subscribe and like this video if you like what I did, and if you stuck around this far, well, thank you. All right, so I'm gonna go, and I'll see you next time.